Hi, welcome. This is a video on section 2.4 from our elementary statistics book about scatterplots, correlation, and regression. This is a fairly short section. It's really just an introduction to scatterplots. And scatterplots are a special type of graph that you can use when you have quantitative data that has both an x and a y value. So you can think of them as points on the xy plane. Okay. So what we're going to be learning about in this video is the analysis of paired sample data. So like I was saying, paired means you have an x coordinate and a y coordinate. So points in two dimensions. We're going to be learning about what's called correlation, which is basically looking at the scatter plot. Does it have a shape or a pattern? That's the essential idea there. And the role of the graph called a scatter plot. And then we're also going to provide an introduction to the use of the linear correlation coefficient. Now we won't actually have to do any math really in this section, but we will be looking at the linear correlation coefficient, which will sort of tell us roughly how much of a pattern there is to our graph. So does our graph seem to follow a straight line pattern, or is it just all scattered all over the place? So that's the idea there. And very briefly, we'll talk about linear regression, which involves the equation and graph of the straight line that best fits the sample paired data. Okay, but this is a very, just a brief introduction to this stuff. So we're not going to actually be calculating the linear correlation coefficient. And in your homework and on your quiz and in the exam, it's mostly just going to be, can you construct a scatter plot correctly? And then looking at the graph, does it appear to have a linear correlation or not? Okay, so I keep saying correlation. Correlation exists between two variables when the values of one variable are somehow associated with the values of the other variable. Okay, so let's jump to an actual picture so we can see what's going on here. This right here is an example of a scatter plot. Now, why is it called a scatter plot? Because we have individual points which represent data values, and they're all scattered around the graph. Now, when we look at this picture here, this particular scatter plot is weighing seals with a camera. Okay, so the horizontal axis, or the x-axis, represents the overhead width of seals. So we're looking at seals from the ocean overhead, and they measured their overhead width of the seals in centimeters. And then they also took those same seals and they measured their weight in kilograms. So on the vertical axis, that's representing their weight in kilograms. Now you can see in this picture, this is an example of what we call correlation. So correlation is the distinct pattern of the plotted points, and that suggests that there is a linear correlation between the overhead width of seals and their weight. So if you look at the word linear, it has the word line built into it. And this is the only type of correlation that we're going to be looking at, is we're just trying to see, well, does this look like it's following a straight line? And obviously it's not going to be perfect, but I think we can see here that this is, roughly speaking, following a straight line. It's difficult for me to draw on this, but, our line might be something like this. So it'd be helpful if I had a ruler, I could draw a straighter line, but I unfortunately don't have one here with me. But that's supposed to be a straight diagonal line. Anyway, that's just a sketch, but we can see that, roughly speaking, the graph is following a diagonal line, even if my diagonal line isn't perfect. a perfect fit to the graph, we can see that the points are all pretty close to that line. Actually, the real line might be a little bit higher than what I drew. Okay. But we say there's a linear correlation because the scatter plot really is following a line. Okay? So we'll see more scatter plots in a bit. So let's go back to the definitions that we're learning. Okay, so like I just said, correlation exists between two variables when the values of one variable are somehow associated with the value of the other variable. But for us, because we're just doing kind of an introduction to correlation, we're just focusing on linear correlation. And once again, the word linear, just look at it, it has the word line built into it. So we're just talking about, well, looking at our scatter plot, does it follow a straight line? It could be a diagonal line with a positive slope. It could be a diagonal line with a negative slope. But it does have to follow a straight line. It can't be any other shape. So linear correlation exists between two variables when there's a correlation in the plotted points of paired data result in a pattern that can be approximated by a straight line. Obviously, it's not perfect. For it to be perfect, every single point would have to be on that line, which almost never happens. It does happen occasionally, but in the real world, it's not going to be a perfect line, right? Okay, so that's the idea with linear correlation. It's following a straight line. Scatter plot, that was, the picture's worth 1,000 words, really, but a scatter plot or scatter diagram is defined as a plot of paired x, y quantitative data. Remember, the word quantitative means that they have to be numbers that measure or count something. We can't have qualitative data, so we can't have categories or names or labels. So it all has to be actual numbers that have mathematical meaning. Okay? Quantitative data with a horizontal x-axis and a vertical y-axis. The horizontal axis is always used for the first variable x, and the vertical axis is used for the second variable y. Okay, so going back to this first scatter plot, we can see that the x-axis is going to be the overhead width, and then the y-axis is the weight of the seals. This one is pretty clearly following a diagonal line that has a positive slope. Of course, you want to always have linear correlation. So what are the other situations that we're going to see? What about this? Well, it already says it down here, but just looking at this picture, there's not much of a pattern here. And certainly, the only pattern we're looking for is, can we draw some kind of diagonal line that's a straight line that fits this graph? And I would say no. I mean, probably the closest thing we could do would be like a horizontal line here in the middle. But because all these points are so spread out, it's very random, and they're just spread all over the place. So what the book says for this particular graph is there's no correlation. Technically, there might be a tiny bit of correlation, but because everything is all scattered everywhere and doesn't really have a pattern that can be approximated with a line, we say that the plotted points do not show a distinct pattern, so it appears that there is no correlation between heights of presidents and heights of their opponents. Okay, so here the x-axis was representing heights of presidents in the United States. This is from the book. And then that's in centimeters. And then the vertical axis actually represents the height of the presidential opponents that they ran against. And yeah, it's very difficult to see much of a pattern here. It's all spread all over the place, so we say there's no correlation. Okay. All right, so we've seen linear correlation, we've seen no correlation. Those are the two primary categories. But obviously there are situations that are in between, this first picture where it's very clearly following a diagonal line versus this picture where there's not really a pattern, at least not a straight line pattern. So there is a middle ground between linear correlation and no correlation. And that middle ground would be, for example, this one right here later in our lecture slides in our notes. So if we look at this scatter plot, this particular example is also from the book, and we're wondering if there's a correlation between shoe print lengths in centimeters, which are the horizontal or x-axis, and then the height of the people in the study, so how tall they are, measured in centimeters. So the reason I'm going to this graph is I said there's sometimes a middle ground between clear linear correlation, this is linear correlation, no correlation where there's no pattern, or you get a situation like this where a lot of these points are kind of on or near a diagonal line, if you will, but then this one down here kind of seems out of place. So with something like this, it's difficult to know that if I did try to draw a line that fit the data, the question would be, would the line go more up here, or would it be going more like this? Because these 2 points here are so far apart, it's hard to tell whether this has a linear correlation or no correlation. So I would say it's in the middle ground. So what they say in the book is it isn't very clear whether there is a linear correlation. So that's why they introduce what's called the correlation coefficient, R. Now we aren't going to have to calculate this, but we're still going to learn about the basics of it. So what it means. It has a long formula, but you can use computers or calculators to calculate it, or in the case of our homework quizzes and exam, it will just be given to you, and then we have to interpret what the correlation coefficient means. So let's go back to this slide. The linear correlation coefficient, R, is it's going to be a number between -1 and +1. It's going to be a decimal, and it measures the strength of the linear association or the linear correlation between the two variables. Okay, and even though we don't have to calculate it, let's learn about it a little bit. So if you do have R already calculated, the computed value of the linear correlation coefficient R is always between -1 and 1. Okay, so like I said, it's going to be a decimal between -1 and +1. Now, if R is close to -1 or close to +1, there appears to be a linear correlation. Okay, if R is close to 0, there does not appear to be a linear correlation. Okay, and then the third case, which is the one that we just talked about, is kind of the middle ground where we're not sure whether there is or isn't a linear correlation. So if R is close to 0.5 or -0.5, it isn't clear whether there is a linear correlation or not. Okay? All right, so if we go back to these 3 different scatter plots or scatter diagrams that we have, this first example of weighing seals with a camera, actually, because it's such a tight linear correlation, and because the slope of the line, it's called the least squares line or the regression line, because the slope of the line is positive, if you look at R for this one, R is going to be close to 1. So we'll just say, just for the sake of an example, I don't know the exact value of r for this, but it would be something like, say, r equals 0.89. Okay. So something like this, this picture here, where we can see a strong linear correlation where all the points are almost on the same diagonal line. Well, because the line has a positive slope, in other words, it's rising from left to right, r equals 0.89 is close to positive 1. Okay? And some people call that positive linear correlation if it's close to positive 1. And then, unfortunately, we don't have an example of negative linear correlation, but I think you can easily imagine, for example, if you have r equals negative 0.95, then it would be like this picture, only it would be instead a diagonal line that falls from left to right. So it would be a diagonal line with a negative slope. Okay, but r equals 0.89 is close to 1. Closer to 1 certainly than it is to 0.5 or 0. So we clearly have a positive linear correlation here. Okay, what about this one? So what about no correlation? Well, again, I don't have the exact data values, but because this one has no correlation, r will be very close to 0. So here, just for the sake of having a number as an example, we'll say here that r is equal to 0.13. Okay, we say that 0.13 is close to 0. It's certainly much closer to 0 than it is to 0.5, and definitely not even anywhere close to 1. So r equals 0.13 is close to 0. And because it's close to 0, when you look at this number, it's telling you that there's really not much of a pattern here that we can draw a straight line through. We can't draw this line that best fits the shape of the data. And by the way, the name of that line is called a regression line. And you can actually do a lot of math to calculate it. It's called the least squares line. But for us, we're just trying to get the idea down. We're not actually going to be doing linear regression. Okay, so we saw close to 1 was linear correlation. Close to 0 would be no correlation. And then the last case would be, for this one, the third scatter plot on our lecture slides. So for this one, they've already actually calculated r. So the value of r that they got was actually 0.59. They wrote out more decimal points, but we're just going to round it to 2 decimal places. So for this third scatter plot here, we've got r equals 0.59. And as you can see, 0.59 is not close to 1, and it's also not close to 0. So the thing that it's closest to is 0.5. And if you're close to either 0.5 or negative 0.5, then that means it's not very clear whether there is or isn't a linear correlation. And we can see that just looking at the graph, right? It's difficult to know exactly where to draw a diagonal line, but at the same time, as we go from left to right, it does look like the average height is increasing from left to right. But then we have this one right here, which kind of seems out of place. So that might even be what's called an outlier, because this data value seems sort of out of place. But anyway, it's very difficult to figure out whether this has a straight line pattern or not, which is why r is actually close to 0.5. Okay, and remember, if r is close to 0.5 or negative 0.5, it's just not clear whether there's a linear correlation or not. Okay, and then so that takes care of the lecture slides. And remember, those are posted on Canvas. And then when you're doing your homework or quiz from this section, the bad news is there are graphs, but the good news is you don't actually have to draw the graphs. They're multiple choice. So the way these graphs, these scatter plots are constructed is essentially you just want to probably arrange these paired data values from smallest to largest. So like here, we would look at the shoe print length because that is the x-axis. So the way I usually do these, if I'm trying to construct a scatter plot like this one here, is when I have these data values, I look for the x-axis. Here the x-axis is the shoe print length. And then I want to arrange these in increasing order, so from smallest to largest. Okay, so without having to rewrite all of these, let me just point out to you, we're looking at, because the x-axis is the shoe print length, we're looking at this first row of the table here. This is a little table that represents our data values. And we want to write smallest to largest. So how do they create this graph? Well, what's the smallest number here on the x-axis? Well, that's going to be 27.6. So our first point is going to be this one. Okay? So you can either just completely rewrite this whole table with everything in order, which is what some people do, or you can number these. So another way of doing it is to number them. So this would be, because this is the smallest x value, this would be number 1, okay, and so forth. So the next smallest x value after 27.6 would be these two values, 29.7. So 29.7, 29.7. So those are going to be number 2 and number 3. Okay, so I'm just looking at the x values, and I'm trying to order everything to make it easier to graph. But the good thing about our homework, our quiz, and our exam is because they're multiple choice, you won't necessarily have to plot all of the points. You may just need to plot some of them, and then because it's multiple choice, you should be able to eliminate answer choices until you see, okay, well, this is the only graph that has the correct points on it. Okay, so after 29.7, we've got 31.4, and then 31.8. Okay, so 31.4 is number 4, and then 31.8 is number 5. Okay, and then you can either just rewrite the whole table, or you can just plot these one by one. So let's just look how they plotted number 1. So number 1 was 27.6 on the x-axis. So as you can see, here's 27, here's 28, and then that right there on the x-axis is about 27.6. And then on the y-axis, this first number 1 is going to be 172.7. So this y-axis happens to start at 172. This next ticker mark is 174. And so 172.7 is going to be a lot closer to the 172. So that's going to be right there. Okay? So that's, as you see, once you have them labeled or arranged in order, then you're just going to work from left to right. So we just did number 1, and then we can get all the other points. Okay, so like the next one would be number 2, 29.7 on the x-axis, which is going to be right about there. Okay, right about there. And then for number 2, we have 175.3 on the y-axis. So that's going to be about halfway between 174 and 176. So that's going to be right about there. Okay, and as you can see, if you do it this way, you can get their next point. So that's this point right here. So as you can see, already we have gotten the first 2 points, and because we have them arranged in order, or at least we know which order to draw the points, we can just work our way from left to right, which makes it a lot easier to graph them. But I feel like it's not too difficult because you're not going to have to graph that many points when you're doing your homework. You just need to look at the graphs and say, oh, okay, well, this graph has a point that's, say, up here, but then when I look at the data values, there are no points that have those values, right? The x-coordinate and the y-coordinate don't actually show up in our data values. So if you had a graph that had this point up here, you would know it's wrong just by a point that doesn't belong with the rest. Okay? So hopefully that won't be too bad. All right, so that concludes this video. Thank you for watching, and I will see you next time.